So hi everyone, thanks for joining us today. And I'm going to share my screen right now with you. So I assume that most of you came here because you are following the data engineering course. If you're not following the data engineering course and you saw our announcement about this workshop on LinkedIn, maybe in the newsletter, don't worry, you don't have to follow the course to also learn from this workshop. But I will quickly explain where all the information that you need for this workshop is. Right, so first of all the content for our course is in this GitHub repo. I will share the link in the description. I will put all the links in the description. Don't worry about that. Right now, I will just show the structure, and then I will share the links, and you will find them under the video. So this is our course, and in the course we have many different topics. And right now we are here. We're talking about data ingestion. And you can just click more details here, and you will go directly to the file we're interested in. So this is the file that Adrien will refer to, I think, but this is the kind of entry point to this workshop. There are some links. I just today added a few links here with notebooks, but Adrien will explain as I think as we go along. And yeah, so you will see everything you need here. It's Data Engineering ZoomCamp Cohorts 2024 Workshops DLT, but the way to go there is just scroll a little bit and click on more details. And I think that's all I wanted to talk about. And just a few notes, maybe like if you're not following the course, still it's okay for you to attend this workshop. You will learn a lot. So you don't have to attend modules 1 and modules 2 to get most of this workshop. So we try to make it in such a way that it's both useful for both the students of the course and anyone who wants to learn about DLT. And right now I'm stopping sharing my screen, and Adrian, the floor is yours.
Thank you. And let me share as well.
Somebody's asking, will this session be recorded? Yes, it will be recorded. I already shared the link in the Telegram channel, and you can just use the same link. So the video will stay available using the same link as we use for streaming. So just click on that link in Telegram or elsewhere where you find it. Just click on that and you'll be able to see this workshop. Can you make the font a bit larger, please? Okay.
Yes, classic problem.
Yeah, that's better. Thank you.
All right. So welcome to Data Ingestion with DLT. This course is not just about DLT. It's mostly about data ingestion. So it will teach you some things that you can do outside of DLT as well. So what we'll learn in this hands-on workshop is how to extract data from APIs or files in a way that is scalable. We'll look at what normalizing this data means and why we do it and how we can do it. And finally, loading this data. And then we will look at incremental loading. We won't look at incremental extraction, which is part of incremental loading, but it's a bit more complex. But I will talk about it more when we get there. So by the end of this workshop, you'll be able to write data pipelines like a senior data engineer, quickly, concisely, scalable, and self-maintaining. And if you don't follow the course and just wanna, oh yeah, that was your line, Alexei.
It's too late now for this line because it's already happening, right? Too late.
The workshop is created in a way that it's self-readable, right? Because for me to be able to do it, I also need bullet points, so you can also follow on your own in case you get lost. So you'll find the navigation, that you have the workshop content, the workshop notebook that I will also show when we get there. And finally, at the end, you'll want to go to the homework starter notebook. So allow me to introduce myself. My name is Adrian, and I've worked in the data field since 2012. I've built many data warehouses and some data lakes and a few data teams. So 10 years into my career, I started working on DLT, or Data Load Tool, which is an open source library to enable data engineers to build faster and better. And I started working on DLT because the data engineering is one of the areas of software engineering where we actually don't have many developer tools. And building better pipelines would require more code reuse, and we cannot all just build the perfect pipeline. So DLT was born to actually enable you to reuse quality code. It's a library that automates the most tedious part of data ingestion. So that's the loading, the schema management, data type detection, scalability, self-healing, scalable extraction. Basically, all the things that make your pipeline break and that make it hard to manage. DLT, we try to make it as a one-stop shop for data engineers, so you kind of have a full toolbox for what you need. And due to its simplicity, it enables starters, beginners, basically to build pipelines 5 to 10 times faster than normal that won't break, basically, that will scale and self-heal. So let's get into the course. I'm following this link here, the workshop content, in case you want to do the same. I already have the notebook open for later. I will zoom it in now. But all right, so many of you have probably worked with files on ingestion, so you've seen them in storage. You know what is actually data loading or data ingestion? It's the process of extracting data from a producer, transporting it to a convenient environment, and preparing it for usage by normalizing and sometimes cleaning or adding metadata. So usually when we're talking about files that are on storage, they've already been put there. They've already been extracted from a source, and sometimes they've been already normalized, sometimes not. You know, basically files in storage to us actually mean kind of already loaded data or somewhere in between.
And if I may add, so in the course, we talk about concepts like data lake and data warehouse, right? The data somehow ends in these places, right? And the process of data loading is actually putting this data there. Am I right, Adrian?
Yes, pretty much. And you know, sometimes the data lake is just a consequence, let's say, of loading to a data warehouse. So people just use it for historization. Sometimes it's the main destination where people use data. So I'm going to use the Pokemon expression while dataset magically appears, because it feels like many starting courses are starting with a file on storage. I think this is also the data science Zoom camp, Alexei. So basically, we want to be the people who will make those datasets magically appear. So sometimes the format in which these files appear is structured and with explicit schema, like Parquet files, Avro files, or a table in a DB, or sometimes the format is weakly typed and without an explicit schema. So for example, CSV, it's a file that other than the header only has data, doesn't really have metadata. Or JSON,
Maybe I will add that this is exactly, like you mentioned, this is exactly what we have in the course. So we have a bunch of CSV files with data about taxi trips, but somebody put this data in a CSV. Right now it's Parquet, it used to be CSV, which we still use. Somebody put together this CSV file, right? It just didn't magically appear out of nowhere. And this is exactly what the case here, this is what we're talking about.
Yes, and in the case of the course now you have Parquet files, which you know I would consider that to be almost loaded data. So you know it's in a data lake, it has a schema, but when you're talking about CSV, a CSV is not fully describing the data. It's just a container for the data, kind of. So actually, data loading often has adding this metadata layer. So let's talk about how we could be this magician. Like I was saying, it's about adding this metadata layer. So for us, it sometimes means adding a schema to the data. So what is a schema? A schema is basically specifying the expected format and structure of the data within a document or data store, defining the allowed keys, their data types, and any constraints or relationships. So to give you an idea, in a CSV, you might have a date time field, but it's not clear that it's date time. You can just tell by looking at it. But a schema would make this explicit, and it would say this is clearly a date time field and it follows a particular format. So we're here to learn about how to make these kinds of data sets available with the correct metadata as well. So we will look into how can we extract this data, so like get those CSV files, how can we normalize, clean, and add metadata, so how can we turn these CSV files, for example, into a Parquet file or a database format, and how can we do incremental loading? So actually, when we build pipelines, sometimes we build full load pipelines, but many times we don't want to grab the whole data history every day. We just want to grab what happened in the meantime. So this would be incremental loading. It would be much faster and cheaper. So what else does a data engineer do besides these things? And what are we not learning in this course? So as simplistic as it seems, actually, the data engineer's main goal is just to ensure that data is flowing from a source to a destination. There isn't really much rocket science around that. But of course, besides building pipelines, running pipelines, and fixing pipelines, an engineer might also need to focus on optimizing data storage, ensuring quality, integrity, cost management sometimes, or implementing effective data governance practices, like continuously refining a data architecture to meet the reporting requirements. Sometimes the data engineer's role will also go to strategic management or enhancement of the entire data lifecycle. So what I mean here is it might even go into, for example, retention policies for private data or all kinds of crazy things around pipelining data. But this workshop specifically focuses only on extracting data and building these pipelines in a robust and scalable way with governance, so kind of with best practices. So you won't be getting much about orchestration or any of the other things. And also something that will be worth learning on your own will be this incremental extraction that will allow you to actually only pull the incremental data that you want. But let's start first with extracting data. And here I prepared also some examples. So let's look at the considerations of extracting data. So most data is stored behind an API. And sometimes this is a web API, like a RESTful API from some business application like Salesforce. Sometimes the API will return a secure file path. So for example, some advertising APIs have really high volume of data like ad impressions. And it wouldn't be reasonable to give you this data record by record to tell you, for each impression. So what they do is they return a file because a file can be read in bulk and it's much cheaper and faster for them to basically make this data available to you this way. It's also more scalable for you to grab it. And sometimes the API is something else. So it could be like a MongoDB or a SQL DB. So basically it might be completely different from a standard HTTP API. So as an engineer, you usually need to build pipelines that just work, that pull data out of these sources and put it into a destination. So here's kind of what you need to consider for extraction to make that happen smoothly and to prevent your pipelines from breaking. So first, you need to worry about the hardware limits. So during this course, we will cover how to manage memory. And what I mean here is, for example, you might be grabbing a very large data source. Maybe it's 4 gigabytes. Maybe you only have 2 gigabytes of RAM. You will want to somehow pull this data and normalize it without running out of memory. So we will look into how we can do that. Then other limitations of getting data could be network limits. So sometimes networks can fail, and generally we're powerless to fix those issues, but what we can do is retry. So we won't really go into any details here, but you can find the docs links of how you could use retries on requesting the data. And finally, there could be source API limits. So each source might have some limit of how many requests we can do per second, like rate limitations. This is usually dependent on the source, and we won't cover this here since we can't really make a good example. So let's look how we can actually extract the data by managing memory, with managing memory. So what kind of limits could be hit on your machine? When you're downloading data, what could happen is that you run out of either RAM or disk space. it's unlikely to run out of disk space. So for cases like these, I would say it could happen on some kinds of cloud infrastructures, but usually these cloud infrastructures will allow you to write to a bucket to mitigate that. So really your main concern is not running out of RAM, because if you run out of RAM, bad things will happen. So let me explain a little bit. Usually you would use an orchestrator to run your pipelines, and many of these pipelines might be running on a shared worker. So an orchestrator might run, for example, 4 pipelines on a single machine. And if your memory runs out due to one of these pipelines, it's going to crash your entire machine. So it's not just going to crash your current pipeline, it's going to crash everything else. So this is why we usually really try to avoid running out of memory. It's the same is true with disk. In most cases, your disk is sufficient, but it can happen to run out. So for those cases, you could just mount an external drive, which should basically be a bucket. So how do we actually avoid filling the memory? Since we often do not know how much volume we have in the data up front, and we cannot use that information to scale, and we also cannot just infinitely scale dynamically, like on the fly. The answer is we need to control the maximum memory. So we do that by streaming the data. The way you could think about it is if we have a giant file, we can't grab it all at once, but we could grab it line by line. We could call this streaming. So streaming here refers to the process, refers to processing the data event by event or chunk by chunk, instead of doing bulk operations. So let's look at some classic examples of streaming where the data transferred is transferred chunk by chunk or event by event. So an example could be outside of the data field between an audio broadcaster and an in-browser audio player. So for example, you might have a radio station and you might be listening to it in your browser. The data gets to your browser through a streaming process. Between a server and the local video player. So for example, on YouTube, when you're watching a video, a little bit of the data is sent. You can already start watching the video, and then the rest of the data is sent while you're already watching. Between a smart home device or an IoT device and your phone. So any kind of sensors, for example, would create some kind of stream of data, and you need to collect it somewhere. Between Google Maps and your navigation app, for example. So this is also an interesting example because, in fact, you get the map and the data in a streaming fashion. You basically don't get all the information at once, but you might get a new route or something like that based on where you are. Also, for example, between Instagram Live and your followers could be streaming. So what actually do data engineers do to stream data? We usually stream data between buffers, such as from an API where data is available to a local file, which is basically a buffer, or from webhooks or event queues into some kind of storage. So for example, taxi rides, maybe at the end of each taxi ride, an event is emitted, and we can capture it and write these taxi ride files. Or from an event queue like Kafka or SQS to a bucket. So this is a classic event tracking case. So how can we do streaming in Python through generators? Let's look at how we can build most data pipelines. So basically, when we process data in a stream in Python, we would be using generators, which are functions that can return multiple times. So by allowing multiple returns, the data can be released as it's produced as a stream instead of returning it all at once in a batch. So we could take this theoretical example. Let's say we have a Twitter search and we look for cat pictures, and we don't know how many cat pictures we're going to get. We might get 10 or we might get 10 million. Are they going to fit in the memory? We don't know that. So to grab this data without running out of memory, we would create a Python generator, and this generator would be able to give us an image, and then we could do something with this image to not have it stored in memory anymore, and then we could ask for the next image. So here's an example of a generator. We can look at the function. So let's say we have a search Twitter function, and we are running a query, and we're saying for each row in our query, so for each result, let's append it to our data list. And if we do this, we're basically filling the memory with our data. So this is just a normal function. It's returning all the data at once. This is no good. So if we want to actually see a picture, we would have to run this function. All the data would need to be downloaded, and then we could see the first row of data. So let's look how this could be written as a generator. This is what the generator looks like. As you can see, it's a little shorter. So basically now we don't have a data list, but we're yielding every result as we get it. So this means that we're actually returning multiple rows here. And when we want to execute this generator, we can basically start running it right away. So what I mean is that the first row that will be printed here will be printed as soon as the first result is ready. So we don't need to fill the memory or wait for all the cat pictures before we can see the first one. So if we actually wanted to turn this generator kind of into a list of data, we could just wrap it into a list and say, my data is this list, and this would basically run the generator and populate the list with data. So let's do some practical examples now. So in the first example, we'll be grabbing data from an API, and we will go to the notebook after I talk about it a little bit to actually run it and understand how it works. So this is the bread and butter of data engineering. So please pay attention and also run it in the notebook. So for this example, we created an API that can serve the data you are already familiar with, the New York taxi dataset. And the API documentation is as follows. There are a limited number of records behind the API, so we won't have any kind of crazy surprises or having to wait too long. The data can be requested page by page, which is a normal way to request data from an API. It's basically streaming micro batches. So each page will contain 1,000 records. And if we request a page with no data, we will get a successful response with no data. So this is our signal to stop requesting pages. So we will be using a get method, using the requests library. We will hit this URL over here, and we will have the page parameter in our request. So how do we design our request there? Like I was saying, we need to get the request page by page until there is no more data. We will yield each page as it comes. And once we have a page with no data, we will stop. So this is how this code would look. We'll go to the notebook soon to run it. And the advantage of this memory is that, of this method of getting data is that we have easy memory management because the API is returning pages. So it's easy for us to just yield these pages and we don't need to break down things any further. The cons are low throughput. So you'll see actually that this transfer is a bit slow because all the data has to go through this API. So let's go to the notebook. And you have here the first cells. You can run them to install DLT.
Maybe can you show quickly how to find this notebook? Because I think
Yes.
this is interesting, and there is no link, so we need to go, yeah, one level up to the DLT file. Yeah, so this is the file that I showed at the very beginning of this, and we have the workshop notebook, which is just a notebook that we have in the repo. It's not a Google Drive, it's not a Colab notebook, but I think this is like if in the resources you have already in Colab. If you scroll a little bit down, yeah, so this is what you put. Course Colab. I think this is the notebook, right? So this is how you can find it.
Yes, this is it.
It's the same, yeah. So this is how you find. So if you want to just get the Jupyter notebook and do it on your machine, you use the first link. If you want to execute it on Colab, which for those who don't know, it's a cloud environment for executing Jupyter notebooks, this is how you do it.
Yes, so the advantage of Colab is that you don't really need to set up anything. and you can just go and run it. This is called magic here. So it basically just allows us to run a CLI
Question.
command.
Before people start executing it, there is a question: do we need to make a copy of this collab notebook, or when somebody opens the link, they can
I
just execute
think
it?
I think you can't change it.
Execute. Mm-hmm.
So you can. So basically, if you are in sandbox mode, so playground mode,
Mm-hmm.
if you see this banner on top, you don't need to do anything. If you don't see this banner, you can basically just open it in sandbox mode or make a copy. Sandbox mode means that your changes won't be saved. So this it enables you to just run it and do things without having to have permissions.
And when I interrupted you, you were installing DLT. Like,
Yes.
did you already talk about DLT? What is it? What is it that we're installing?
So I talked about it a little bit.
Mm-hmm.
Mm, I guess it's a loading library. It's the first of its kind. It's basically a tool made for developers to help them load data much faster. So myself, I was a data engineer and I felt the need for this tool because we didn't have actually anything that allows us to easily build pipelines. So for example, we have tools like Airbyte. They are kind of like, they come with pre-built sources and you can easily in the UI build some things using their building blocks, for example. But if you really want to build a custom pipeline that can do anything, you need to go to code. And this is actually where most of us end up eventually because there are many different APIs with different, let's say, ways to get through them. And it's very hard to actually create a generic solution that works for everything. So DLT, by being a library, gives you the option to do whatever you want in a custom way and then hand that over to DLT. So the advantage to you actually is that DLT has a schema inference and evolution engine. So it will look at the data that you're passing to it and automatically normalize it and load it for you. So you'll see it basically makes this loading part very easy.
Mm-hmm. And there is a question. I don't know if it's the right moment to ask this question. We can postpone it. Up to you. The question is if DLT is an alternative to Mage or any other workflow orchestration tool, or it's something that
Yeah,
is.
DLT is not a workflow orchestration tool. It's a pipeline building tool. So specifically, how does that fit with Mage? Mage is an orchestrator that is using sources from basically a framework that's called Singer that was created for software engineers. So what that means is that if you want to maintain the sources that you're running with Mage, that might be a bit unpleasant, but you could also run just DLT pipelines on Mage, and then you would benefit from both, basically.
So if I can rephrase and summarize your question, answer is that we use a workflow orchestrator such as Mage to run DLT. So let's say we have a cron job that we want to execute hourly, right? And we want to use DLT for talking to some API and loading data to our data warehouse. And then we would just invoke it from Mage.
Exactly. So DLT is actually the first data loading tool that was made to fit in existing orchestrators. Almost all the previous tools kind of either need to be patched into an orchestrator in a funny way or live outside of the orchestrator completely. All right. Shall we get into the extraction? All right. So so I already prepared the code here for the first generator. And as you can see, I was telling you we have a URL. We're making a request with a page number. And this is how we handle the pagination. So we start from page number 1. And as long as we have data, we will just keep getting pages. So if we have data, we'll yield the data and we'll increase the page number for the next request. If we don't have data, we stop the loop. So this means that basically we will start from page 1, and as we get data, yield the data, and if there's no more, we'll just stop. So we can just run this now, see how it would look.
Can we also close table of contents? It kind of takes too much space.
Thank
Yeah.
you for that.
So what's happening? So right now we're talking to the
Yes.
API and it responds with something, right?
Yeah, so basically we're sending this request to an API and we're increasing the page number with each page. And as you can see here, it got the first page with 1,000 records and it printed these 1,000 records. So it's actually like a lot of data here. Don't scroll too far. Until finally we got to page number 11, which had 0 records. So we just stopped trying to grab any more data.
And this is data with taxi tips. So this is the same data we use for the course, but also if you're not taking the course, it's the data with start and of a taxi trip and then some other information.
Yes.
This is like Uber or whatever.
Exactly. And you'll see it in a bit more detail soon when we load it. Right now, as you can see, it just looks like JSON, kind of, or like a document. And for example, if you look at the time here, there's nothing to say that this is ISO timestamp, right? It's just a string in this case. Anyway, let's go back to the course and continue. So this is kind of like an example of a very classic API. It will return pages, and if you just yield these pages, you can do something with them. You can process them incrementally, you can load them. So let's look at the second example now, which is grabbing data from the same file, but this time we just have a simple file download. So there's no more API. The advantage of getting data this way, I would say don't do it this way, but I'm showing it to you anyway. So you can remember that this is not the best practice. You don't have to follow along in this part. So I will start telling you about it. Some APIs basically respond with files instead of pages of data. And they do this because it's much cheaper to just give you a file link than to give you a page of data. Because when they give you a page, they need to actually read the data, put it in a different format. So basically, the better way for some apps with a lot of data to offer you this is through files. And if we just download this file as we normally would, the big advantage is that we have a high throughput because the file download is fast. But the con is that we would be using memory to hold the data from the file. So this would pose a problem if we have a small memory and a big file. So this is what the code would look like. Like I said, you don't need to run this code. It's just a simple file download. So as you can see, we have the JSON-L file here. And this is just a generic downloader. We get the data, we split it because JSON-L is basically lines of JSON that we can split. And then we can return this data. So clearly this is bad. Basically in the response, we will have all the data. In this structure, we will have all the data again. So if we have 4 gigs, we'll have 8 in memory if we have 4 gigs in the file. So don't do this, like I said, but if you're going to run this code and you're going to print this data, you're going to see that it takes quite a while before we get the first rows because the entire file needs to be downloaded. So now let's look at the best practice way to download the same file. I would say for this one, let's go to the notebook afterwards and follow along. So here it's the same file, but we do a streaming download. And the advantage is that we keep the high throughput. Now we also have memory management if we do it in a row by row way, in a streaming way. The disadvantage of doing it this way with files is that for columnar formats, it's not easy to do. So what I mean is that if we have a file that stores the data in rows, we can split this file into rows and we can start processing the rows incrementally. But if the file is storing the data in columns, then actually these columns are stored in blocks. So we would need to request blocks of data until we have a complete row. And then we would be able to get the first row out. And then we would need to keep requesting blocks and processing them. So for this workshop, we just have a JSON-L file, so the easy way. If you need to do the hard way, you can definitely find ways to do it online. But basically, this is the same file that we're downloading, and this time we're downloading it with stream equals true. So this means that when we are reading this response, the data doesn't have to be all there already. So we can start reading from it before the file has been downloaded. So we can basically just iterate through the response. And if there is a complete line downloaded, then we can yield it. So basically, yeah, we would just be running a simple method. And let's move on to the notebook to see what this looks like. So this is the bad way, and I will run it anyway, just to show you. It took some time. There will be a time print. Okay, so it took a couple of seconds to print the first piece of data. And let's run the third example, which is, okay, that was fast. So basically in this example, we're getting the first rows of data and already printing them. And as you can see, it took 0.08 seconds. So like less 9% of a second, right? To get this data versus 2 seconds above. So you can clearly see that there is streaming happening under the hood and that the first records are available to us immediately.
But the distinction here is that, like maybe if we execute the entire thing end to end, maybe for the second one, the time will even be more, right? Than for
Yes,
the first one. But the speed, like how quickly we process the first line and how much memory we use doing that is way different. So it's way faster and
yes.
way lower
So
memory.
it's not even about speed, right? It's about overall, it's about scalability, because if suddenly our file is really, really big and our worker stays constant, then at some point we'll run out of memory. So while this approach might be marginally a little bit slower because we have a bit more function calls and we're working over chunks instead of working over one big chunk, it will work, whereas the other one might just break, right? So as a data engineer, your responsibility is to deliver data every day correctly. So it's better if your data is 1% slower in download than if it breaks every now and then. All right, so let's do a short parenthesis here and load some of the generators from above. So what I did here, I just, so we won't spend a lot of time looking at this. It's just a quick run. So basically, I'm importing DLT. I'm creating a pipeline, which is just a connection to a destination. And then I'm giving these generators to DLT to run them and to extract them. And the reason why I'm showing you right now is because we were on the topic of streaming. And what is important to know here is that DLT will respect this streaming. So if you pass it a generator, it will take out the first data that comes out of it. It will start working with it and before requesting the next item. And basically, DLT will create something we call extract packages that we can change the size of. So if we have really little memory, we could say we want every 1,000 rows to write to disk, and this way we wouldn't be running out of memory. The default setting on DLT is actually quite low, so you probably won't run out of memory unless you're running on some really, really tiny Raspberry from 5 years ago or something.
Maybe we should talk a little bit about DuckDB. So this is where we write, right?
Yeah,
So in the course, we don't cover that. So in the course, what we do in the week one, we cover Postgres. And maybe Adrian, you can say a few words. What are the main differences between these two? And I, in the meantime, will run a poll. I'm quite curious to know how many of you know DuckDB. So I'll just quickly run a poll. You just say, oh, have you
So
heard about
I'm
DuckDB or
gonna,
not?
sorry. So I'm going to talk about what happened here, how the data made it into DuckDB, what DuckDB is, and why we like DuckDB. So basically, as you can see, I put this generator to go into a table name called HTTP download, and I put this other generator to go into another table name called stream download. And now we run this against DuckDB, and we can see the tables here, and we can see the data in the tables. So what is DuckDB? DuckDB is an in-memory analytical database. You might have heard before of a database called SQLite. It's also an in-memory database. SQLite is probably on every mobile device by now, right? It's because it's an in-memory database, you can do a lot of embedded applications with it, really cool things. DuckDB is similar, which means that you can basically just run it in process. So use it in your pipelines. It's not an actual persistent database like Postgres in a way. It's more like you can spin it up in the process and refer to some files, and you have a functioning database. So what is actually happening when we're loading data to database to DuckDB is we're creating some files underneath of data, and then DuckDB is just in the Python process able to read this data. So basically, this means we can use it in Notebook. And this is part of the reason why DLT Hub really likes DuckDB. Basically, like I was telling you, DLT is a library that it can run almost anywhere. So DuckDB is also a library that can run almost anywhere. So because DLT needs to load data to a database and DuckDB is available anywhere, we can easily showcase DLT, right? So we have quite a few, let's say, notebook demos where we run it. We also have some setups where we do some small calculations with DuckDB. We don't use it for anything big, but in theory, you could do something with DLT, load the data to DuckDB, and then read it from there and send it forward to a different database. So for example, here we're reading the data that we just loaded. We could actually transform this data or summarize it and put it in a new pipeline, for example, to some other database.
And I just see the results of the poll. So 64% of people who voted do not know, have not heard about DuckDB. So you can think about DuckDB as a kind of, well, I don't know, I don't want to say as a data warehouse, but for our course, you can think like you can write data to BigQuery, which we covered this week, or some data lake, like a bunch of files on Google Cloud Storage or S3. So you can think about DuckDB as a different way, right? As an
You
alternative that you run locally.
You can also think about it as development mode. So a very normal way for us is that we do pipeline development on DuckDB and iterate on it quickly because it's right here in front of me. I can just use it anywhere. And then when I'm ready to go to production, I just switch from DuckDB to BigQuery.
It's exactly like
These-
SQLite is used, right?
yeah, exactly. And with DLT, you don't need to care about the database. It's basically database agnostic. So if it runs on DuckDB, it's going to do the same thing on BigQuery. So this is why we use it as development mode.
So the usual flow would be, let's say I'm developing something with DLT. So I work on things locally and I use DuckDB for testing. And let's say I write some integration tests, whatever, with DuckDB, right? But then when I go to production, I just say instead of writing to DuckDB, I write to BigQuery. And that's the only thing I change, right? The
Exactly.
pipelines, like all the code I write stays the same. The only thing I replace is the destination.
Exactly. Like we even use DuckDB on GitHub to test our pipelines, right? On CI runs. Okay, let's continue with the next part, which is normalizing data. This one is quite demonstrative, like we need to understand some concepts that are happening there. So you often hear about people spending lots of time cleaning data. Now, what does this actually mean? If we look into it granularly, we'll see that it's usually two parts. One of them is normalizing data without changing its meaning. And another is filtering, for example, taking out outliers when you're building a model and they might actually disturb something. But this changes the meaning of the data slightly. So part of what we often call data cleaning is just metadata work. So what we're usually doing is adding types. So we're turning strings into numbers, strings into timestamps. Sometimes we're renaming columns because SQL databases have kind of like a standard naming convention and you can't just put anything. Sometimes we flatten nested dictionaries. So when you have dictionary in a dictionary, we try to bring it to the same level so you don't have multiple data structures and it's easy to access. Sometimes we unnest lists or arrays into child tables. So basically, just like you can have a dictionary nested into a dictionary, you could have an array nested into a dictionary. And unfortunately, an array cannot be flattened because it actually represents multiple data items at a varying amount. So it's actually a separate data structure that we need to break out if we want to keep it as a table. So we will look at a practical example next, as these concepts can actually be quite difficult to visualize from text. So why actually do we prepare data? Why don't we just use the JSON as is? So for example, many database engines support just throwing some JSON in there, or we could turn everything into string and just put it into a text field. So why don't we do that? So the problem with just using JSON is really a transfer format. So it doesn't describe the data much. We don't actually know what the JSON document contains until we scan it. Types are not enforced between rows of JSON. So for example, we could have a record with age 25, or we could have a record with age 25, or another one with age 25. One could be an integer, one could be a decimal, and one could be a string. Or in some systems, you might actually have a dictionary for a single record, but a list of dicts for multiple records. So an example of this is the Discord API, where if it's sending you a single message, it will send you a row of data, but if it's sending you multiple messages, it's going to send you a list of rows, which is a different data type. So this kind of thing can easily lead to applications breaking downstream. So also, when we want to use JSON data, we cannot use it easily. We generally have to typecast it. So we would have to convert all these timestamps and say what their format is. It's very tedious. Reading JSON also loads a lot more data into the memory because the whole document is scanned. So when you have a really large document, if this document was Parquet and you were reading a column, you would be able to just scan that column into memory. But with data like JSON or CSV, you couldn't do that. You'd need to basically scan the entire row, and then you'd be able to get your value. So this has implications regarding memory usage, but also cost. So reading JSON, okay, I've already said this. So JSON is not fast to aggregate, simply because it has to be parsed up front before we can do anything with it. It's also not fast to search for the same reason. Basically, JSON doesn't have anything a modern database might have, and it's a lowest common denominator format for interchange. It's not really suitable for direct analytical usage. So I'm giving here a practical example where I made some changes to the New York taxi data to include some of these more complex structures. So what I did was I added a nested dictionary. So a nested dictionary is basically a dictionary within another dictionary. We added nested lists. So nested list is basically a list that contains more elements. It could be rows or it could be just values. We also added a record hash because we'll use this later for incremental loading. So this is what our final record looks like. And as you can see, this is kind of like what you'd expect a normal JSON coming out of an API to look like. It's pretty nasty. If you want to use it, you can use it, but you'd need to figure out how to get all your fields flattened. And the places where you have these lists, you'd need to kind of create new tables for them. So introducing DLT will accelerate data normalization massively because it basically automates it. So we created DLT with the purpose of assisting data engineers to build simpler, faster, more robust pipelines with minimal effort. One of the problems that you typically have when you're building an API data pipeline is that the response is not documented. So actually, you'll spend a lot of time sifting through JSONs like these and trying to understand what to do with them. So DLT completely removes that effort because it will infer the schema from the JSON documents and do it for you. So you can think of DLT as a loading tool that implements the best practices of data pipelines, enabling you to just use those best practices in your own pipelines in a declarative way. It enables you to stop reinventing the flat tire and leverage DLT to build pipelines much faster than if we did everything from scratch. And what I mean here about the flat tire is that, frankly, there are, a limited number of business applications, and people build the same pipelines over and over and have the same problems over and over. So it would be nice to not have the same problems again. So DLT automates much of this tedious work, and it does it in a way that is robust. It will do schema inference and evolution. It will alert changes to the schemas. So if you have new columns or if a data type changes, you can alert that. And you can use the schemas as data contracts. So for example, if you're ingesting events and you decide that you only want to accept events with a specific format, you could say that, and it would reject anything in a different format. DLT will type your data, it will flatten structures, rename columns to fit databases, so it just automates everything to load the data. It will process the streams of events or pages without filling the memory, and it can basically handle a variety of DBs or file formats. So let's use it to load this nested JSON to DuckDB, and let's go to the notebook. Oh, I already started running it. So this is the JSON that we have. As you can see, it looks pretty bad. We have a pipeline here to load the data to DuckDB, to the taxi rights dataset. And we've run the pipeline here. It did load. And let's look what the data structure looks like. So something that is a bit difficult to illustrate is basically that there is a relationship between these tables now. So we will have a passengers table because this is how the data is represented in the input. And we will have a stops table, and there will be a relationship between the passengers, the stops, and the top level data. So here we have a little DuckDB reading script that basically shows us what tables we have. Then it will show us the rides table. Then it will show us the passengers and the stops tables. And finally, this is showing how we could join the data back together if we wanted to have it as a single data set. So as you can see, there is a parent column and a record hash created that we can use to rebuild the data structure. So you can see here the rights table. In our case, we just had one row of data, so you can see everything now is properly typed. We have the passengers table, which basically just has the name and the rating, and the rest are backbone columns. And as you can see, this DLT parent ID will refer to this DLT ID here. So you can basically just join the data back. And it's the same is true for the stops table. You have your helper columns, you have your latitude and longitude, and this is what the joined data would look like. Of course, this is the Cartesian product of the three tables, so this is why you have 4 rows. Yeah, so basically you can see, let's look at what happened to the nested dictionaries. And you can see somewhere these columns with 2 underscores. And if we look in our input data structure for coordinates, so you can see basically this was flattened into the parent structure. So longitude from the start of the trip, from the coordinates, will have become coordinates start lon. So this makes it easier to use the data later. All right, I think that was it for this part. And now we have a really short part. Oh, if you are following the course from GitHub, you will note that there is a CLI command you can run. I won't run it now since I'm not prepared for it, but if you run this, it will open a Streamlit app that will show you the tables that were loaded. So let's move on to incremental loading. This section is quite short. So incremental loading is the act of only loading new data. So this means that as we update our data sets with new data, we would only load the new data as opposed to making a full copy. But sometimes we might be replacing some of the destination data. So if the data was updated, for example. So by loading incrementally, we are making our pipelines run faster and cheaper. And unfortunately, this also introduces some complexity. Nothing is for free. So incremental loading goes hand in hand with incremental extraction and state, two concepts in which we will not dive right now, but you should definitely check it out after the workshop. So state is basically the information that keeps track of what was loaded. So when we have an incremental pipeline, we have basically some kind of checkpoint from where we need to continue. So state is basically keeping track of this checkpoint to ensure that once you're starting again and want to load the next increment, you know where to start. So this checkpoint actually could be stored in multiple ways. It could be, for example, last updated date. It could just be an ID that was incremented. It could be many ways. And finally, there's also incremental extraction. This concept is about using the state, so your checkpoint. So let's say you know that your last loaded value was 3 days ago, and you could send this value to your source extractor to only request data from 3 days ago. So you're both only extracting the data that you need and only loading the data that you need. And you can learn more about the incremental extraction on the DLT docs.
Do I understand correctly? Let's say if we talk about the example with a file. So let's say there is a file, and every time we request the files with the writes for today, there are new writes because like the day goes by, right? And then during the day, maybe there are new writes appearing, right? And what we want to do is like maybe each hour, look at this file and only process things that were added since the last run, right?
Exactly.
But the file is large, so that there is no way for us to say easily, okay, we already processed this, we haven't. So we would need to write a lot of logic, right?
Yes,
To
I
handle
mean,
this.
it's also a cost thing, right? Because let's say you're incrementing your pipeline every 5 minutes, it's a typical pattern for streaming pipelines, right? You might have a stream with a buffer and then you take micro batches from it. And if you were to scan your destination table every time, you'd generate a ton of cost. I've actually done that by accident in a previous project, and I managed to generate about 2,000 euros worth of cost to copy one MySQL table into BigQuery. It was a big mistake. That set cost alerts.
So there's a question. So DLT is a tool for parsing JSON and putting it into a data warehouse.
This is one of the things that it's really good at doing, yes. I would call it a one-stop shop for data engineers looking to load data. So while this is the core of what it does, it has way more around it. So let's look at how we can incrementally load data, because you were mentioning, Alexei, about the appends, and I was talking about updating data, which we call a merge type of loading. So the way you can think about loading data is, first of all, can we extract this data incrementally? Because if we can't extract this data incrementally, then it doesn't really make sense to talk about incremental loading. Because, then we could, most of the time is spent on extraction anyway, not on actual loading, right? So what we really want to make sure is that we can extract the data incrementally. And what this means is we need to know either what is new or what changed. So this depends on the source, if the source will tell us. And depending on whether the source is immutable or whether it's subject to change, we might have to use a different strategy. So what does immutable mean? So you were talking about taxi rides, and we could say taxi rides don't change. Like once a ride has happened, it has happened. Nothing can change about it anymore. This would be immutable data. It's event data, for example. And this kind of data we would just append. So is it stateful data? No, it's events. So we would just use append right disposition. So we would just keep track of what was loaded and get everything from that point. But if the data was stateful, so for example, let's say we are loading some information about the car, and the car might get damaged, or the car might be out of order, or the car might be in maintenance, or I don't know. Then the car has a state, and basically from one day to the next, the car could become unavailable. So in our case, we are giving an example where the event doesn't have a state, but the rating of the riders does. So we will look into how to change that. So basically, if your data is subject to change, then you cannot just append it. You need to update the data at the destination. So this means either you have a way to request the data incrementally, and if you do, you can do an incremental loading pipeline, and you will use the merge disposition, or you cannot request it incrementally, in which case you're just going to replace everything because you don't have a better option. So the merge operation is actually, the way it works is it uses an ID to identify a single record, and then it will replace any records it has in the new data. Sorry, it will replace any destination records with the records it has in the new data. So we will do an example together with a piece of data that we were looking at earlier. And what happened here was it looks like the payment status got changed from booked to canceled. And maybe Jack, the passenger, likes to fraud taxis. We're not entirely sure, but his rating also went down. So this merge operation replaces an old record with a new one based on a key. This is why we added the record hash earlier. So we will use the record hash to identify the record. So this way we can, basically the SQL database will know it's the same record that needs to be replaced. So like I was saying, a merge operation doesn't actually update the rows, it actually just replaces them. So this is the reason why we're not updating is because updating would be a columnar operation and we're using analytical databases. Updating would be a row-based operation and we're using columnar databases for which this would be very slow. So instead of updating the rows, we will be replacing them. So like I was saying in this example, a couple of things have changed. So basically this rating here and this status. And I will switch over to the notebook to run this example and discuss how the data was updated. I'm not sure where I had it. Okay, sorry, this was actually, did I already run this? I'm not sure. Okay, no, I didn't already run this. So now we updated the data and I'll show you basically what is the difference from above. So I was supposed to do a merge here. Now we've done a merge. So this was actually, sorry, I had a mistake in the course, but you have to say right disposition merge on the primary key record hash. And what this will do, basically, it will replace any records with the same record hash with whatever we have in here. And as you could see from before, we have our data here. So we have the payment status booked and we have the ratings somewhere. Here we have the passenger rating 4.9 and 3.9. And if we look at the updated data, we have 4.4 and 3.6 for ratings. And we have the payment status booked. I think I made a mistake. Okay, there we go. Now the payment status will be canceled. As you can see, and basically this updated your data. So this is what we have prepared for this course. We kept this course quite simple to cater to everyone and to make sure that everyone can complete it. But you can find here some bonus snippets if you'd like to check them out. This is an example of how you can load the same data to a Parquet file. So here we're using FS spec. It's basically a file system spec that allows you to use local folders or a bucket, or I think Google Drive also supports it to write files. Here is an example of how you would load to BigQuery. So basically, like I was telling you, I'm just changing out my destination when I'm developing. So in this case, we'd have to install the right library and authenticate to BigQuery, and then we'd be able to load this table. So before this course, I was running it and printing the data back. As you can see, there is a built-in SQL client in DLT. So basically, regardless of what type of database you're using, you can just use this client to get some data out. So it's really great for development. What else? Yes, and you can find other demos in this repository and on our blog. Both DLT users and our working students create demos here. So you can check them out. And this is finally, this is the documentation piece that will give you an overview, a little bit of the DLT capabilities. So if you want to learn something more advanced, I suggest starting here and just looking at what you can do. There's a GPT Docs helper button on the docs, so don't miss that. It will answer most of your simple questions. And if you get stuck, you can just join our community and ask questions there.
Yes, you finished, right? Thanks,
Yes,
Adrian.
I finished it. I prefer to have it a little shorter and
Yeah,
have time for questions. And I
yeah,
also,
we have a lot of questions. Um, so when you showed now the example with incremental loading, so there is a question if how different incremental loading from CDC. CDC is change data capture. What's
okay.
the differences between these two?
I would say it's similar but different. So in CDC data capture, you're basically getting a stream of updates from the source database, and then you need to have some kind of system by which you parse these updates out of there, and then you can apply them to your tables. So I would say fundamentally it's the same. You have a data source, you have a destination, but you have additionally some kind of mechanism to transform this stream into tables. So we're actually looking into adding that for SQL databases, right? But it's not about the tool, it's about the source and destination process.
And another question also is about this example, but more like about the specifics of the example. How is the record hash calculated? Is it different every time you update the record, or is it more like a unique
Yes.
identifier?
So in this case, I created it by hand, right? But depending on what your data source is, you will typically have some kind of identifier. If you don't have an identifier, you can basically create some kind of hash out of your row. If you have to update your row, so you cannot use your row to create an identifier, then you're screwed, pretty much.
So I guess like you have a record and you know which fields in the record are not going to change most likely and which are going to change. So you can base the hash on the records that do not change. And you
Yes,
know that the next update, they will stay the same. Maybe
yes.
it will, like you need to think how to make it unique, but that's one of the possible options.
Exactly. Basically, the way you can think about it is you need an identifier, and that identifier could be created out of some columns.
Then there is a question about other tools for parsing JSON. So there was a discussion in the live chat, and later, sadly, we will not have access to the live chat. It will be lost. So maybe this is something we can talk about too. So there is a question in the live chat, like, are there alternatives for DLT for parsing nested JSON? And somebody mentioned pandas, but then there is a discussion like, okay, pandas do not really do this exploding, meaning like when you have a list inside of a dictionary, like it doesn't create an extra table that you can link.
Yes.
Do
So
you
I would
know?
say
Yeah.
yes. So, when we built this tool, we looked at everything that was out there. I would say pandas is the closest thing. Um, there is nothing else that is just good and open source and just runs. So this is part of the reason why we built it.
Because with pandas, uh, if I remember correctly, what it's doing is when you parse it for nested things, you still have a dictionary, and for nested list, you have a list, and then you need to kind of parse it again, have some logic for creating like another data frame, an extra
Yes,
table or
you could
whatever.
do this, and you need to make sure that you're pushing some kind of record key from the parent record into the child table, right? So you still have can recompose the data. The problem is, you can do it as a simple one-off, but we're loading pipelines, with dozens and hundreds of tables, and I don't think it's reasonable to um, use pandas here. Also, pandas loads everything in memory, so it would break the streaming concept.
Okay, there were questions. I took some note. I think we mentioned, so what if an API has restrictions to, let's say, producing only 100 records at a time or having some rate limits? I assume DLT handles these cases
So
too, all right?
DLT has built-in requests library that you can use. I'm not sure if we're using it in this. No, I didn't want to introduce the complexity here, but you have it here, for example. So basically, this is a drop-in replacement for the request library. And if you use this, what it has extra is retries. So when you're making HTTP calls, some of them are retriable. So for example, there could be a server error, or there could be a network traffic issue, or it could be that temporarily you're not allowed to grab the data because of a rate limit. So what this request replacement will do is it will have some kind of incremental backoff to retry by default. So if it cannot get the data now, it will try again after half a second. If it still doesn't, if it still can't grab it, it will try again after 2 seconds. And usually it can eventually just get it and resume. But it depends very much on the source API. So you might need to do some, private management of how this works.
I am muted, but as we speak, I'm making changes to this DLT markdown file. So if I may, I want to share the screen because we also have a homework for that. So you will see, this is the document we shared at the very beginning, and the workshop content was here. So this is what Adrian was showing all the time. But then if you scroll down, you have the homework section. So this is where you can, after watching the video, you can try to implement something yourself to make sure you understood the concepts. So there are 4 questions, and then this is the link where you can submit it. I just edited it right now. So like as usual with other homeworks, you will see this form where you submit like the answers to your questions. So the due date is in 2 weeks. So you have is it in 2 weeks? In 10 days. Yeah. So you have enough time to actually do the module that we have right now that starts today. So the due date for that module will be in 1 week. So then you have a bit of extra time to actually focus on that workshop specifically. Then you will not have any other deadlines. Right? So then you can just do that. So this is the homework. I showed how to find it. I think that's all I wanted to mention. Yeah, so this is the starter notebook that you can use. I don't. And then, yeah, there is one more question that I forgot to mention. There's a question how DLT is different from DBT.
Yes, so DBT is there to transform data, DLT is there to load data. So DBT comes from data build tool. It's once you've loaded data with DLT, you can use it to create a nice analytical model for that data. DLT is basically made to work very well with DBT, but it won't help you transform data. You can actually run DBT with DLT. So when DBT was built, it was built to be set up in a way that is, let's say, not very Python user friendly. So if you don't actually want to set up running DBT in your project, you could just run it with the DLT DBT runner. You can find it on our docs, and that will basically inject credentials directly through Python, make your life a little easier.
And if we talk about ELT, extract, load, transform, so DLT is like the EL letters, right? And DBT is
Exactly.
the T letter.
Exactly. But since DLT is a Python tool, you can, also do transformations in Python if you really want to, like not with DLT, but your custom transformations. So we see people do all kinds of things, but generally they just use it to throw the raw responses directly to the database, and then they run DBT to work with the data.
Yeah. Did we talk about how to give you a star? Did you show? So somebody asked if DLT is an open source project, and the
Yes, it's
answer
an
is
open
yes.
source project. Please go to
And
the site.
yeah, please show us everyone so everyone knows how to give you a star.
Okay, let me share the screen.
In case somebody doesn't know how to do that, I'm sure like this is what we showed in our first intro lecture. We showed how to give a star to our data engineering course repo.
Nice.
So yeah.
So, if you are on our website, don't miss the GPT button over here. And to star us, click on the star us link at the top.
Helpful.
It will take you to GitHub. You still have to do one more click. It doesn't work, just from clicking the link. So you still have to click on star here. Another thing that I might suggest to you is we have a blog, and in this blog, we have all kinds of articles from people. So, for example, this is a user. Sometimes we have learners that are creating articles. If you decide to do any kind of personal project and you want to showcase it, we'll be glad to showcase it. So just, join our Slack and let us know, and we'll either feature it on our blog or something like that.
Okay. And for everyone who is watching the video, which is 382 people, well, excluding me watching from my smartphone, please like our video. It will help with the algorithm. YouTube will spread this video so more people will actually get to see this. So please do that. Yeah, I don't know what else to mention apart from thanking you and the entire DLT team for putting this together.
I would say that's it. And DLT is an open source tool. So if you want to write about it, if you see something on docs that you don't like, you could actually just click edit this page, right? And you'd be able to do your first contribution, open source contribution. Or, we have people that, so I can't encourage you to build and donate verified sources, but if you are particularly brave, you can also try that.
Okay. Yeah. Well, I guess that's it then for today. Thanks a lot, Adrian, for preparing the workshop. Thanks everyone for joining us today. If you're watching live or if you're watching on replay, thanks for your time and have fun. And again, if you have any questions, ask it in our Slack, or there is you also have a channel for this, or like you can join
No,
DLT
you
Slack.
can just join our channel. It's on top of the web page, and you'll find the technical help channel. You can ask questions there.
If you watch this video after the course is over, you might not get support in our course channel. So then this is definitely when you need to go to the DLT Slack, and this is when you will definitely get support. Okay,
Right.
then I guess we are wrapping up 10 minutes earlier. So I'll go get some tea, and
Sounds
you
good.
probably
Yes,
also
of course.
keep
Thank you.
talking for so long. So yeah, have a great rest of your day, and see you soon.